Hello everyone and welcome back again to the linear algebra component of the Calculus and Linear Algebra series. In the last video we introduced this idea of how complex numbers can act on the complex plane in an additive way. That is, we showed that we could think of complex numbers acting via addition as shifting the complex plane in a combination of left and right and up and down. And the natural question now to ask is to say, well, is there a way in which we can talk about complex numbers acting on the complex plane in a multiplicative way? That is, can we multiply two complex numbers and how can we interpret that geometrically? Well, we've already seen to some extent how the imaginary unit acts on the complex plane in a multiplicative way. That is, we saw that when the imaginary unit acted on the real numbers, it simply rotated that real number line by 90 degrees in an anti-clockwise direction about the origin. And we also saw that the imaginary unit can be thought of as acting on the imaginary number line in a multiplicative way by simply rotating it again by 90 degrees anti-clockwise about the origin. So the natural question then to ask is, given any two complex numbers on that plane, is there a way that I can multiply them, or is there a way that I can think about, given a single complex number, how does that act on the entire plane via multiplication? So that takes us to our first kind of picture here, or animation. So we're going to drag up here our picture of the complex plane. And the first thing that I want to think about is how does the real number line act on the imaginary number line? That's the first thing to discuss, because so far we've only talked about how the imaginary unit acts on the real number line and the imaginary number line in a multiplicative way. But how do the real numbers act on the imaginary numbers in a multiplicative way? Well, we saw in an earlier video that the real numbers can be thought of as to act on themselves in a multiplicative way by simply stretching the real axis kind of by a factor of whatever that number was, or squishing it in some way. So let's take here, say, the number 2. Well, we can think of the number 2 as acting on the real number line in a multiplicative way, as stretching the real number line by a factor of 2. So if we look at the imaginary number line, and we look specifically here at just the number I, how can we think of the number 2 acting on the imaginary number line? Well, it simply just stretches the imaginary number line by a factor of 2, which is fairly clear, right? If 2 acts as kind of stretching the real number line on itself, it would make sense that 2 acts on the imaginary number line by stretching the imaginary number line by a factor of 2. And we can see that here, exactly in this picture as well, that kind of arrow stretched from pointing at I now to where 2I used to be. And similarly, we can also talk about, well, what happens, say, if we take something like a half here. How would a half act on our imaginary number line? That would simply squish our imaginary number line by a factor of 2. So we see that the real numbers simply act on the imaginary number line by stretching and squishing it in a multiplicative way. And we then might ask, well, how does an imaginary number act on the real numbers in a multiplicative way? Well, we've seen how it works for the imaginary unit. The imaginary unit simply rotates it by 90 degrees. So you might expect, well, let's look at the number here, 2 times I. Well, what that's going to do is, if we take here, again, kind of the number 1, or we take the vector corresponding to the number 1 on the real axis, and we want to say, what's the action of 2 times of the imaginary number 2I on the real axis? Well, that's simply going to stretch the real number line by a factor of 2, and then rotate those numbers by 90 degrees counterclockwise about the origin. So that's here we're thinking of 2 times I as simply kind of I, the action of I, namely we're rotating by 90 degrees counterclockwise, and the action of 2, multiplicative, which is stretching. In fact, we saw it the other way around here. We first stretched and then rotated, but we see that it was the same either way. We could first rotate and then stretch. Those things are identical. In other words, what we're showing here is 2 times I is the same as I times 2. Okay. Well, let's have a look again at maybe some negative imaginary numbers. How would the negative imaginary numbers act on our real number line in a multiplicative way? Well, again, we can think of this as first stretching by a factor of 2. So that's kind of corresponding to this term 2. And then we want to think of it as acting now multiplicatively by minus I. Well, minus I acts on this multiplicatively by rotating it clockwise by 90 degrees, because we think of minus I acting multiplicatively as a rotation by 90 degrees clockwise. If I is a rotation by 90 degrees counterclockwise, minus I is a rotation by 90 degrees clockwise. So in other words, we're thinking here of how the imaginary numbers act on the real numbers. All they simply do is they just stretch them and then rotate them by 90 degrees, right? We can see that from these animations that we've drawn up here. So our question then would be, is can we extend now our real action of our real numbers onto the entire complex plane? Well, if the real number line acts on the imaginary number line by simply stretching it, and the real number line also acts on itself by simply stretching it, and both of these are considered in this multiplicative way, it would make sense that the real number line should act on the entire complex plane by simply stretching it by some scale factor. So if we look at the number 2 here, it would make sense that a general notion of kind of how would 2 act on the entire complex plane in a multiplicative way, it would simply stretch the entire complex plane by a factor of 2. So that's exactly what we're going to have, right? That's our geometric picture. And similarly, if we think about how would 2 times I act on the entire complex plane, well, we saw that it kind of acted on the real number line by stretching it and then rotating it by 90 degrees. So it would make sense that it acts on the entire complex plane by rotating it by 90 degrees counterclockwise and then stretching it by a factor of 2. Now notice, much like before, we kind of got this property that 2 times I was the same as I times 2, so we want to see that geometrically. In other words, if we first now stretch by a factor of 2 and then rotate by 90 degrees, that was exactly as what we had before. So we're thinking of the imaginary numbers acting on the complex plane as rotations by 90 degrees, either clockwise or counterclockwise, depending on the sign, and then stretchings of those scale factors. So the natural question to ask then is, can we talk about the multiplication of 2 general complex numbers? So here we've got 2 complex numbers on the plane. We've got z and w. What would it mean to say how z here, say, acts on w multiplicatively, or how w acts on z multiplicatively? In other words, what's z times w and w times z? Well, if we think about how we'd kind of defined the imaginary numbers acting on the complex plane, we realize that what we actually did is we took the complex plane, we rotated it by the argument of the imaginary numbers. Well, the argument of the imaginary numbers, at least if the real part is positive, is always pi over 2 or 90 degrees, right? Which is why we got this 90-degree rotation. And then we stretched it by the modulus of whatever that number was. So if, for example, we had 2 times I, the modulus of 2 times I was simply 2. So when we saw 2 times I acting on the entire complex plane, it rotated it by its argument, that was 90 degrees, and then stretched everything by a factor of 2. And when we saw it for minus 2 times I, that rotated it by 90 degrees clockwise about the origin, and that's because the argument of that is minus pi by 2, and then again stretched it by a scale factor of 2. So in other words, the complex or the imaginary numbers were acting on the complex plane by first rotating it by the argument of that complex number, and then stretching it by its modulus. So let's see if we can extend that idea. That idea extends now to 2 random complex numbers. So in this situation, let's think about what happens now if we've got w acting on z. Well, using that kind of idea, we first rotate the vector that corresponds to our thing z by the argument of w. So that is, we're going to rotate it about the origin by whatever the angle is that w makes with the real part, positive real part of the axis. So that angle there is exactly what we've rotated this red vector here, z. And then we're going to stretch it by whatever the length of this green vector is, which in other words gives us this thing here. And that is exactly what we think of as w times z. So w times z, we're saying that's how w acts on z multiplicatively. In other words, it rotates z by the argument of w and then stretches it by the modulus of w. And similarly, we can see the other way around. We want to maybe see that w times z is the same as z times w. So that is, if we think of what is z acting on w in a multiplicative way, that is that we take the green vector w, we rotate it by the argument of z. In this case, the argument of z is 45 degrees. We can see that, right, because we've got a triangle width 2 and height 2. So we rotate the green vector by 45 degrees. Notice we rotate it counterclockwise because the argument is positive. And then we stretch it by the length of the red vector. And that takes us to exactly the same point that we had before, right? In other words, this is exactly z times w, what we define as z times w. And we see that's equal to w times z. In other words, we see that the multiplication on complex numbers is commutative in this geometric way. Okay, so removing these and just thinking about the number z now, how can we take this complex number z, how would it act on the entire complex plane? So let's kind of generalize this notion. We've seen how the imaginary numbers act on the real numbers. We've seen how the real numbers act on the imaginary numbers. And we've seen how one complex number acts on another complex number, all in this multiplicative way. How would a single complex number act on the entire complex plane in this multiplicative way? What we saw is that it would rotate the complex plane by whatever the argument of that complex number is. So that is, we start off by rotating the entire complex plane by 45 degrees, or pi over 4 radians, because that's exactly what our argument of z is here. So we first rotate, and then we stretch it by the scale factor, which is the modulus of z. In this case, the modulus of z is going to be 2 root 2. So we stretch it by 2 root 2, and that's exactly what we get. And we can see here that by looking at this picture, what we've got that the point that used to be at the point 1 is now at the point z. In other words, z times 1 is z, right? This makes sense. And similarly, we can see that we could do the operation the other way around. In other words, we could first stretch by a scale factor of 2 root 2. So that gives us kind of this picture, and then rotating by an angle of 45 degrees counterclockwise, or pi over 4 radians, which exactly gives us the same picture as before. In other words, these operations are commutative. So can we write this down algebraically now? Can we kind of write down what it means given two algebraic versions of complex numbers? What does it mean to multiply them? Well, if we write them down in polar form, that's kind of what's much more useful here, at least with this geometric picture. If we have our complex numbers in polar form, and we've said here that we take our complex number z, where its modulus in this situation I've said is r1, its argument is θ1, and we take another complex number w, in which its modulus is r2, and its argument is θ2, then its complex multiplication is exactly what we've just seen here geometrically. We simply add up the angles, so we've got θ1 plus θ2 in the kind of cosine and sine terms, and then we just multiply together the moduluses. So if we want to think of it in the kind of way of the other picture, if we had that z was equal to r1 cosine θ1 plus I sine θ1, then acting w on it, in other words w times z, would, well, let's do it in the way that we can first stretch that number by the scale factor of the modulus of w. In other words, we would multiply it by r2, which would give us the r2 r1 cosine of theta plus I sine of theta, so θ1. And then we simply add on the angle, which is the argument of w, which in other words gives us these additions of θ1 and θ2. So this is exactly what we've seen on this geometric picture, and it translates nicely into this algebraic version. So if you want to calculate it algebraically, you can do it this way, or you can also visualize it in this geometric way. But the next question is there a way in which we can also write down an algebraic way of multiplying two general complex numbers, but in this Cartesian form, not in this polar form? So whilst this polar form is kind of really easy to derive by kind of from the geometry, is there a way that's kind of easier to do algebraically, but not so easy to see geometrically, using the Cartesian form of complex numbers? So kind of thinking in that line, what I want to do now is I'm going to take the complex plane here. I'm going to remove all the points, so we're not thinking of these as kind of 1 unit along or 2 units or whatever. They're just kind of general points in our complex plane. We've labelled them here by the imaginary real axis. And we'll take another kind of random complex number here, which we're going to label as c plus di. And we can see here actually from this picture that c is in fact a positive real number and d is in fact a negative real number, which will actually tie specifically into how we're going to kind of see how to prove the product of two Cartesian forms of complex numbers geometrically. And we can write in the vectors, the kind of corresponding vectors coming from the origin for these two complex numbers with a kind of red and green arrows here. And the first thing we want to say is, well, how can we do w times z? Right? How can we think of w acting on z? Well, we've already seen that now in this previous picture, so let's kind of just do that in this kind of initial way of kind of thinking about rotations and stretchings. That is, we take this red vector, z, and we would rotate it by the argument of w. Notice here now we rotate it in a clockwise direction because the argument is negative, because in this situation our complex number w is in this kind of bottom half of the complex plane, so therefore its argument is negative, and that means we're rotating clockwise, not counterclockwise. So that's our first thing, and then we want to stretch it by the modulus of w. In other words, that takes our vector up to here. And we're going to label this point here now. This is w times z, and we're going to leave that yellow dot there. So that reminds us of kind of how we constructed w times z using this kind of rotation and stretching picture. In other words, using this kind of polar form picture. But instead, is there a way in which we can get to this point w times z purely just using the values of c and d and z, right? So we want to see, is there a way of constructing from these vectors a way of getting to w times z just using CD and z. Well, starting in that line, let's rotate first this vector, this red vector, by 90 degrees, counterclockwise. Well, what is this vector, right? Well, we should know what this vector is. That's simply I times by z, because we know if we act on a complex number by the imaginary unit in a multiplicative way, that rotates it by 90 degrees counterclockwise about the origin. So we're going to label that as I times z and shade it in blue now, because that's going to be useful. So I times z, we've taken z, we've rotated it by 90 degrees, that is the same as I times by z. Now, what happens if we take I times z, this blue vector, and we multiply it by the imaginary component of the complex number w? That is d. Well, in this situation, d is negative. So if we multiply it by d, that's going to be corresponding to multiplying it by -1 and then multiplying it by minus d in this situation, because d is negative. So multiplying it by -1 would rotate it by 180 degrees, and then multiplying it by the minus d factor would stretch it by some factor of d. But in this situation, in this particular picture, d happens to be 1, so it's not going to stretch it in any way. So multiplying that blue vector by d simply rotates it round by 180 degrees, and that gives us, in other words here, our diz. This picture would generalize to any corresponding w of c plus di. This has just been picked so the vectors just don't run off the page. So if d here was not happened to be 1 in my situation, it would just stretch that vector by whatever that factor of d was. If d was less than 1, it would squish it in some way. And if it was positive, it would have just stretched it and not flipped it round by 180 degrees. But because it was negative, it flipped it round by 180 degrees, or pi radians. So now we say, well, just using c and z, is there a way that we can get to this point wz? Well, what we notice is, well, we don't need to think of this vector at z, this red vector, as coming from the origin, right? We can just shift it down so its kind of base now is at the tip of this blue vector. And if we stretch this red vector along now, we realize that if we stretch it by some scale factor, that gets us to this point here, which is w times z, which we saw previously as kind of rotating and stretching. Well, what was that stretching? What is this new kind of longer red vector we've got here now? Well, we realize that is simply just c times z. So what have we got here now? We've realized that we can write w times z, which is the same as z times w. We've seen that, in other words, the operation is commutative, is the same as diz plus cz. So we can write that there, right? In other words, I've kind of written it here in a different way with the addition. The addition is also commutative. That is a plus b is the same as b plus a. So in this situation, we've got cz plus idz. In other words, if we write z now as a plus bi and expand that expression, we have a kind of closed form, or a nice algebraic form for the multiplication of two complex numbers in this Cartesian form. So you can do this yourself at home by pausing the video. If you write in here z as a plus ib, we've already got here that w is c plus di. If you substitute in z equals a plus ib into that expression that I kind of derived above, and multiply out all the factors and combine together all the imaginary parts and real parts, you get exactly what I write down here, which is this ac minus bd plus I times ad plus bc. And you might even realize that if you multiply these brackets out, that's the same as what you would normally do by multiplying brackets out for the real numbers, but just with the relation that I squared equals -1. So there's kind of this connection between this useful algebraic way of multiplying things, but really all it translates to in this geometric picture is multiplying by complex numbers just corresponds to rotating them and then stretching them by the modulus of that complex number. So what we've seen here now is we've extended our idea now of multiplication to complex multiplication, and where we thought of multiplication in the real number line as kind of stretching the number line or squishing it by some scale factors, what we see in the complex plane is that complex multiplication corresponds to this kind of stretching and squishing action that comes from the real numbers, but also rotations that comes from the imaginary unit, effectively the imaginary numbers. So multiplying two complex numbers effectively just corresponds to rotating one of them by the argument of the other and then stretching it by that modulus of that one. So that's where we're going to conclude the video. And in the next video, what we're going to do is we're going to look at complex division, and we're also going to look at something called complex conjugation. Now, these things in a geometric setting are very easy to see. Complex division, we're just going to think of as the reverse of complex multiplication. And Complex conjugation is simply just going to be a fancy way of saying that we reflect our complex numbers in the complex plane in the real axis. So if we just reflect it in the real axis, that gives us this idea of complex conjugation. So I remind you as well to read the notes alongside this. There's some more examples in there of how you multiply complex numbers. This should hopefully give you a kind of more visual aid for seeing how to multiply complex numbers, how to think about this stuff geometrically rather than just in this kind of algebraic setting, and also to attempt any problems in the module handbook related to this video. So thanks very much for watching, and I'll see you in the next video.